Okay, all right. So let's start. So this course is digital electronics, and before we delve into the details of this particular course, a little bit about background about digital circuits. So before electronics started, if you wanted to do some computation, you had to do it using mechanical means. For example, this is a mechanical computer. Some of you may have heard of it. This is a working model of it. So before 20th century, if you had to do any computation, any calculation, electronics was not there, and you had to do it by mechanical means. So a set of wheels and levers and all that were used to carry out computation. And if you want, you can read more about it. You can see this particular big machine that you see here was used to add 7 numbers of 31 decimal digits. As students, if you wanted to do calculation, now you all have calculators. People used to use something called slide rules. And, if you wanted to do multiplication and division, I've never handled it, but I was trying to get one. And apparently, at this time, if you want to buy these, people are asking for thousands of rupees for these slide rules because they've become antique items here. All right. So anyway, so as students, people would use slide rules to do multiplication and division and other operations here. Anyway, these are interesting that before the electronics age, this is what you had to do. We all know that electronics revolution started with the invention of the triode. This person, Lee De Forest, is credited with having discovered this particular tube. It was a vacuum tube with 3 electrodes, anode, cathode, and grid. The interesting thing about this particular device was that by applying a voltage to the grid, you could control the current that was flowing between anode and cathode. And that resulted in an interesting property of transconductance, that current flowing between these 2 terminals could be controlled by a 3rd terminal. And this was a totally new device. Before that, such a device had never existed. And with this particular device, of course, with the triode, one could do, in principle, lots of interesting things. One could build amplifiers, oscillators. And in the context of digital circuits, using triodes, one could build an inverter. All of you are familiar. If you apply a low voltage, you get high. And if you're high, you get a logical low. So you could build an inverter. You could build a NOR gate. And all of you know from your previous background that NOR gate is a universal gate. And therefore, any logic you could implement using NOR gate. I've not shown an AND gate. You can implement NAND gate as well. And if you have 2 NOR gates, you can cross-couple them. And you can build a latch also. And you know that this is a storage element. So in principle, with the triode, one could do processing of information. You know, a logical NAND or a NOR, with that logical operation, you can do whatever you want. You can do all arithmetic operations, multiplication, division, whatever you're thinking of, you can do that. So you could do processing of information. And with the latch, you could do also storage. And as I said, communication was possible because you could build amplifiers and oscillators and modulators and all that. So communication was also possible through the triode. And therefore, the triode was a revolutionary device. It could enable a new form of communication over long distances. It could enable processing of information and also storage of information. And the triodes sort of reached their peak towards the end of 1940s. And this is an example of what people could do with a triode. This is an example of a computer, 1946 ENIAC, and you can read the details of it later on. The peak of vacuum tubes was when you could integrate. You can see about 17,000 vacuum tubes. 17,000 vacuum tubes, 70,000 resistors, capacitors, and all of that. 5 million soldered joints. But you could see that, well, you could do all of that, but see, look at these things also. 30 tons. You can see that it occupied the entire room, 30 tons, 160 kilowatts of power. And it was not a very reliable system. The tubes would burn out, and about 50 tubes a day on an average had to be replaced. So this was the status of course, this ENIAC could do things that were beyond imagination as compared to mechanical computers. It had a very good computational capacity, but you can see that it was not very easy to do that. And so although what we talk about information revolution, that you can process information, communicate information, store information, all of that was possible in principle, but not easy, as you can see here. And so the next step in the evolution of electronics, as all of you know, was the transistor, 1948. And so this is a early picture of how transistors were sold. You know, one would put a transistor next to a vacuum tube and say, look how small it is, right? So the transistor was pretty small, miniature as compared to a vacuum tube. You know, could operate at very low voltages and consumed very little power, and had all the properties that, in principle, all the properties that a vacuum tube had. It also exhibited transconductance. You could make amplifiers, oscillators, all of that, logic operations, everything you could do. And it was much smaller, consumed much less voltage, much less power, and therefore, this is an example of what you could do with the transistor. Early calculator, one would say, Sharp calculator, 1964, was a revolutionary product. So imagine something that occupied an entire room now could fit on a tabletop as a result of the invention of the transistor here. Again, you know, 530 germanium transistors, diodes, and all that. Again, you can see that although from a room to a tabletop, but still, just look at the numbers: 25 kgs, and what else? Power, 90 watts of power. Okay, so still it was not very convenient. And imagine this is only 530 germanium transistors, and it's occupying an entire tabletop. If you had to integrate, let's say, 10,000 transistors, what would happen? All right. So integration level was better, much better compared to a vacuum tube, but still very limited in terms of what you could do. Now, calculator, this early calculator that you see is an example of what we call as a discrete circuit. Discrete circuit in the sense that what you do is, the components here are transistors, and what you do is you take all these transistors and you interconnect them on a printed circuit board, right? A PCB. So you integrate them and you make a circuit. And what is the problem with this particular method of fabricating circuits? You see this transistor here. The transistor that you see here, all of you are familiar with it. You've held it in your hand. You've put it on your breadboard. You've done this. The transistor itself actually is very small. This shows a bipolar transistor. Similarly, MOS is actually very small. But because of the way we fabricate circuits, we have to pick a transistor and place it on a printed circuit board. The pick and place method requires that either I or a machine has to hold the transistor. And therefore, even if it is very small, you have to actually make it large so that a machine or a human being can actually hold it, can pick it and place it wherever you're making the circuit here. So the transistor, even though very small, is packaged and made into a big entity. The transistor may be only, let's say, 20 micron by 20 micron or 10 micron by 10 micron, let's say in early cases. But the packaged transistor is about a centimeter in dimension, right? So you have to deliberately make it large because of the way we fabricate. We have to pick and place, right? So as an example, let's see, if you're trying to, so this is the method of fabrication of circuits. I'm talking about 1950s or so. 1948 transistor was invented, and after that, till about 1960 or so, this was the method of fabrication. You would take transistors and integrate them on a printed circuit board. So as an example, let's see, if you want to make an 8-bit adder, the kind of difficulties that we'll get in. So if you want to make an 8-bit adder, so the idea here is that we have two inputs, 8 bits here, and you add them up and you expect a sum, also 8 bits, and you expect a carry out. And so this is the adder that we want to design. And as we'll see, a very simple way of doing this 8-bit adder is that you take a full adder. Full adder is nothing but it adds up 3 bits. Okay, 3 bits. I've not shown an input bit here. So it's a 3-bit adder. 3-bit adder. This shows actually, this is one input, and another input. Produces a sum and produces a carry. So what you can do is, you can take full adders and you can cascade them, 8 of them. And thereby each one of them works on 1 bit. And so if you take 8 of them, you get an 8-bit adder. Right? It's a very simple way of making an 8-bit adder out of a full adder here. Let's look at a full adder. Don't worry about the details here. So full adder, well, I can implement it using gates. So one possible implementation is shown here, NOR gates and NAND gates and all that. Okay, so you implement with gates. Each one of these gates is implemented with transistors. So this is an example of an implementation using MOS transistors, NMOS and PMOS, CMOS technology here. All right. There are various ways of implementing it in this particular implementation, not the most efficient, but the number of transistors are 36. So each full adder implemented with these gates, eventually when you translate them into transistors, turns out to be 36 transistors. And so each full adder is 36 transistors, so your 8-bit adder will become 36 into 8, hopefully this is correct, 288. So our entire full adder, 8-bit adder circuit is 288 transistors. So let's try and make a PCB out of it. So we are going to make the traditional way of making this adder would be to take all these transistors, integrate them on a PCB. All right. So we didn't make a PCB out of it, but we have shown a small PCB here. And this is one transistor that you see here. So what you'll have to do is put all these transistors that you see here, and you'll have to wire them up. You have to interconnect them up. And roughly, if you look at this particular one, there's only a partial part of a PCB. So if you look at this particular one, what you find is that there are 24 transistors here in this small part here. And roughly, if I measure the dimension of this particular box here, which encloses this 24 transistors, roughly it's about 10 centimeters square. 3 centimeters here, 3.3 centimeter or so. Okay, roughly 10 centimeters square. So I have 24 transistors divided by 10 centimeters square. So my density when I'm going towards a PCB, my density, transistor density would be, let's say 2.4 transistors per centimeter square. Now, if this is the density, and if I were to make this complete 8-bit adder, then we can calculate my overall area may turn out to be 120 centimeters square. 288 divided by 2.4, 120 centimeters square would roughly about 11 centimeter into 11 centimeter. All right, so this 8-bit adder, you can imagine now a PCB, 11 centimeter, how big that is. It would occupy that much particular space here. And obviously, each one of these transistor weighs, the PCB board weighs, so it's going to be reasonable weight, and it's a reasonable size. And you can easily imagine this is only 288 transistors. Now you imagine 1,000 transistors or a 10,000 transistor here. Let's say, just for the sake of argument, if I were to integrate 24K transistors, 24,000 transistors, that would occupy roughly a space of 1 meter by 1 meter. So what this particular example is showing, yes, transistors are small, but in order to make this circuit, I have to deliberately package them and make it big. Each becomes a centimeter. And then, therefore, when I integrate a large number of transistors to make a complex circuit, the circuit occupies a large size here, 1 meter by 1 meter. So pretty soon, although the transistors were invented, people were very excited. They immediately could see that there is a problem of integration. How do we integrate large number of transistors in order to make complex circuits? So immediately people could see, and the response was the invention of the integrated circuit, a new way of making circuits. This was 1958. Two independent researchers, Jack Kilby at Texas Instruments, Robert Noyce at Fairchild, both of them independently came up with the idea. And the basic idea was the transistor is small. We need not package it and externally integrate them. What we can do is we can make the entire circuit on the silicon or germanium silicon itself. So we can make the transistors and we can interconnect them and make the entire circuit on silicon itself. So that's why, by the way, every circuit is an integrated circuit. What we mean by this integrated circuit is a more appropriate word. These things are interesting bits of information that one can see later on. What we mean by integrated circuit is what a better word would be monolithic integration. Mono means single and lithos refers to stone, which means on a single piece you're not just integrating, you're making the components and you're interconnecting them. So in this early example, Jack Kilby is talking about, he was making a circuit with some resistors, capacitors and transistors. So he was saying that you can make the transistor, you can make the resistors, you can make the capacitors on the silicon chip itself, and you can interconnect the nodes. And thereby you can reach the whole circuit would occupy a much less area, and other benefits also come here. And the invention of integrated circuit was revolutionary, new way of making circuits, which we'll see, which enable you to integrate more and more number of transistors here. And eventually, the importance of integrated circuits was recognized and was given a Nobel Prize in the year 2000, the invention of ICs here. All right, let's look at this method of making circuits here, which we call as monolithic integration. So let's go back to our traditional example, that 8-bit adder that we were talking about. This 8-bit adder, so this was a full adder, this was the circuit here. And if I were to make this entire circuit, this is only a full adder circuit. If I were to make it on chip, it would look something like this here. On chip implementation of the full adder here. I'll show this in a little bit more detail here. So the idea is that if I were to do that, and depends on the technology that you're using. I'll come to that, what we mean by technology. So in this case, the example that I'm looking at is a 1 micron CMOS technology, which 1 micron refers to the minimum dimension that you can create using that particular technology. Minimum width of a wire or a gate or whatever. Okay, so 1 micron is the minimum width that you can do. And under this technology, this full adder would have a size of 66 micron by 48 micron here. So let's blow this up here. So this is our full adder here. Now, we'll go into details later on, but just for a quick discussion here, you see this green region here, and a red region here. The red is polysilicon and the green is N+. So what you're doing is you're making a transistor here, and you're making a transistor here. There are 2 NMOS transistors here. There are 2 PMOS transistors here. This is a place where you're connecting a metal to N+. And then you're connecting metal to N+, and you're connecting the PMOS to the NMOS here. So my point is that you're making the transistors on the silicon itself, and you're interconnecting them also on the silicon itself. Earlier, remember, each transistor was made and packaged, and then you interconnect them on a PCB. Now you're making it on silicon itself, all the transistors that you see here. And each transistor is very small. Each transistor is very small here, and then you're interconnecting them also. So I can take this is one full adder here. I can take 8 of them, and I can connect them up. There are 4 of them here and another 4 of them here. One can interconnect them. I'm not shown the spaces used for interconnecting. The whole thing would measure, if I were to make it on silicon itself, the whole 8-bit adder would measure 270 micron by 100 micron, roughly. I don't want to argue too much about these numbers, but roughly 270 micron by 100 micron. Now, you can make this 8-bit adder, but it's not useful still, because it's very small. How do I handle it? How do I use it in some system? Right? So I have to package it again. So eventually use it in some system. I will have to take this IC that I've designed, 8-bit adder IC, and I will have to package it. So, for example, one could take you can see here, I have 8 bits here, 8 and 8, 16 plus 8, 16 and 8. So what I've done is I've taken I think this is a 28-bit IC, a 28-bit package, and one can take the whole adder that we have designed, place it in this particular IC here, and connect the appropriate pins and that you see here, connect the appropriate terminals A and B to various pins, and you need VDD and ground and all of that also. So we can take this one, and if we take this particular package, this is an example of what we call as a dual inline package here. There are 2 rows of pins here, 1 row here and another row here. And in these are old packages. We have much, much better packages now. In these older packages, the pitch, the distance between the 2 pins is about 2.5 mm. So since we have about 14 of them, roughly the size of this particular package is 35 mm. And on this side, the size is about 7.62 mm here. So when I take a different method of fabricating my 8-bit adder, not the traditional discrete circuit, but I make it as an IC, internal size is very small, 270 micron by 100 micron, but eventually when I package it, it's still very small, 35 mm by 7.62 mm. So we have 2 different ways of making circuits now. A discrete, which we said here, 11 centimeter into 11 centimeter that you see here, and we have an IC, way of making an IC, which is 35 mm into 7.62 mm. All right. Now, although I've shown here 288 transistor circuit, I could potentially put 1,000 transistor circuit here, and still the size may not increase that much, because there's a very weak relationship between how many transistors are there inside and what is the size here. You note that the size here is 270 micron into 100 micron. The eventual size is not what this size is. The eventual size is actually the size of the package, and the size of the package is determined by how many pins that are there. Okay, so the eventual size depends on something else, number of pins and how good your packaging is and all that. So I could pack 500 transistors and still it may look about the same size. All right, so once the integrated circuit was invented, of course people took advantage of it. The fact that now you can more readily integrate larger number of transistors and make complex circuits. So this is an example of early complex circuit, Intel 4004. 1971, 4004, first 4-bit microprocessor. And this integrated 2,300 transistors. They were all PMOS, and the technology was 10 micron. Minimum dimension that one could do was 10 micron, and this was the technology here. Now compare this, the integrated circuit microprocessor versus, this is the size here, versus the ENIAC. As commented by some, that it had the same computing power as the first electronic computer, ENIAC, that is there. All right, so integrated circuit, the invention was revolutionary. New way of making circuits, new way of integrating transistors and making them, a miniaturized circuit here. All right, so if you look at the history of electronics, we'll come more to that. So it's been a case of increasing integration. All right. Now, the problem is not solved as yet. Well, increasing the level of integration is still a challenge. I just showed you that you can make all the transistors and interconnects, and therefore you can integrate large number of transistors. But the problem is not solved, so let's look at that. So this is roughly the example of Intel 4004, the first microprocessor. As I said, it had roughly 2K transistors, 2,000 transistors, and the size of the die, or the chip, was 10 millimeter square. Roughly, for the sake of argument, let's say 3.3 mm by 3.3 mm. 2K transistors. Obviously, the first microprocessor was 4-bit, very elementary compared to what microprocessors are now. So you would like to make a more complicated circuit, more complex microprocessor. So let's say I think of a nice design, and for that I require 64K transistors. Okay, really ambitious. From 2K I want to go to 64K. So if I use the same technology, 10 micron technology, what would happen is roughly the size would become something of this kind. Each 2K, I can take 64K and I can put 2K, 8K here and 8K here, and eventually arrive at a 64K array of transistors. Okay, and the size would become, if I just add up 4 multiplied by 3.3, 1.32 centimeter. This is another 1.32 centimeter. Again, not very large, right? 64K transistors crammed into 1.32 into 1.32 centimeter square. Looks pretty small, but there's a problem. I can't it's not trivial to just take transistors and pack them up, because what happens is once you increase the size of your IC, there are other problems that come up. And for that, so the die size here, if I multiply 1.32 into 1.32, I think it will come out to be 174 millimeter square. So we've gone from an IC size of 10 mm square to 174 mm square. What are the problems that come if you simply pack more transistors and do that here? Well, to do that, we need to look at a little bit about IC economics here. Okay. Well, you can design an IC, you can package it. Eventually, you have to sell it. Somebody has to buy it. If nobody is ready to buy, well, it's not a successful design here. So, if we look at a cost of an IC, okay, cost of an IC is when we are talking about it, it's a very simple model. The idea is to convey certain concepts here. So, the cost of an IC would be, well, you've spent certain amount of time and resources to design that particular IC, right? You've hired people, designers, and you have to pay them and all that. So there's a development cost. And the development cost divided by the number of ICs that you eventually sell is one, which we call as the non-recurring cost. And then there is a recurring cost. For each IC, of course, you have to make it on a silicon and all that. There's a recurring, which we call as a production cost. So the IC cost is made up of two parts. The non-recurring part, one-time cost, versus for each IC you have to incur certain cost here. So let's look at this particular part here. The second part here, the production cost, the actual cost in production. So the production cost of an IC is the cost of the die, the silicon chip. Another name for a chip is the die here. The cost of the die, the cost of the package in which you put that particular die, and the cost of testing it. The cost of testing it. You can't simply fabricate something and send it to a customer. If the IC is not working and the customer gets it and puts it in his system and doesn't work, your whole reputation will go. So you have to test and make sure that the IC is working properly, right? So die cost, packaging cost, and the testing cost here. So die cost, let's look at the cost of the die. So you don't make a single IC. What you do is you process an entire wafer, a silicon wafer here. And on that particular silicon wafer, you would have hundreds of dies that are there. And what would happen is you can see here, you have hundreds of dies here. What you do is you dice them up. That's how the word die comes here. You dice them up, you cut them up, and each individual die, you package it, and then you have to test it. So what is the cost of the die, of one single die? The cost of the die will be the cost of processing the wafer divided by the number of wafers which are good, the yield, right? If you process 100 wafers and only 90 of them are right, so eventual cost will go up by cost of the wafer divided by 0.9. So this is the cost of the wafer divided by the yield of the wafer. How many wafers are, there's no damage, there's no contamination, the wafers which are working here. So that's the cost of the wafer here. Divided by, what is the cost of the die? How many dies do you get? Total number of dies that you're able to get. And what is the yield? How many of the dies are working? Okay, so how many dies do you get? A rough idea of how many dies you will get is the area of the wafer divided by the area of the die, area of the IC. But you can see here, not all the area of the wafer is covered with dies here, especially at the edges here. And besides, there are some test circuits and all of that. A rough rule of thumb could be that about 85% of the area of the wafer is available to you in the form of a die. So 0.85 times the area, this number may vary. So 0.85 times the area of the wafer is available for die divided by the area of the IC. So that's the number of dies that you get. And, while you are making the wafer, you go and probe each particular die. There's some simple test that you run, this is not that particular test that I'm talking about. This is wafer probe test. So on the wafer itself, you go and probe each particular die, and you know which dies are working, which dies are not working. So this is the yield. How many dies are working? Okay. So for example, the number of dies may be 500, but the number that are actually working may be 400. Okay. So the cost of the die is cost of the wafer divided by number of dies that you get multiplied by the yield. All right. So let's look at some numbers here. Now, what is the problem? You can immediately see here that as you increase the area of the die, in the previous example, remember, we went from 10 mm to 174 mm. So what is the consequence? The consequence would be I'll get less number of dies, and eventually the cost of the die will become higher. But there's even more serious problem. Obviously, if you occupy more of silicon area, the cost increases. But there's more of a problem. And the problem comes about that as you make the area of the die larger, this yield that you see here, it also goes down. And to understand that, there's a simple picture here. On the wafer, what happens is, as a result of inherent defects and also defects which are introduced during the processing, there are defects that are there. These black spots that you see here. And this is an example of a die. If the defect happens to be there in that particular area, what may happen is one or more transistors may fail. It may be an open circuit or a short circuit or something like that, a catastrophic failure. And therefore, this particular die will not work. So there are defects on the silicon wafer itself, and that's a fact of life. And because of that, you get some dies which work and some don't. In this particular case, you can count, I have 20 dies, and this one will be defective, This 4 of them will be defective, so I have an yield of 80%. 16 out of 20 work, and I have an yield of 80%. Now suppose I increase the die area. Die area becomes large. I've made them really large. What is the yield now? I get only 2 of them working out of a 6. Yield is only 33%. So yield in general goes down as you increase the area of the die. And therefore, only 33% are working. Only 2 of them are working. So first of all, as you increase the die area, its cost, number of dies that you get decrease. And the other problem that occurs is that the yield goes down. And therefore, what this is translating into is that the cost of the die is becoming higher. And if the cost of the die becomes prohibitively higher, then you can't market it, you can't sell it. There won't be enough buyers for it. Let me give you an example here. As a rough rule of thumb, people say the cost of the die increases as area of the IC, area of the die multiplied by to the power 4 here. So, all right, this is a old example taken from this particular source here, which gives you an idea. Some more realistic numbers are there. So the cost of a wafer in this particular case, so this is talking about 16 MB DRAM manufactured using 0.35 micron technology. Okay, the cost of the wafer is $1,180. One wafer is costing that much to process. You know, all the processing that is involved here. And the wafer is 200 mm. 200 mm translates into, I think, 8-inch wafers here. The die size that they were talking about, 16 MB DRAM, the size was 54 mm square. So 54 mm square, if I take, number of dies that are available are 476. Actually, if I simply take the area of the wafer and divide by 54 mm square, I will get 581. Simply, if I take the area of the wafer and divide by 54, I'll get 581. But I said all the area is not available. So actually, how much did they get? 476. So the ratio is 476 by 581, 0.82. That's what I was telling you. Roughly about 0.8 or 0.85%, 85% of the area may be available in the form of a die. All right. The number of good dies. So 476 was what was available. After yield was 80%. The number that was there was 380. Yield was 80%. So the number of good dies were only 380. Each die was packaged. The cost was 0.4, package cost. And then the assembly and then the testing cost, 0.6. And final test yield, so the total cost of producing that 16 MB DRAM was 4.36 here. So you can see this is the, we said there are 3 components. This is the wafer cost divided by total number of dies that you get, 380. Packaging cost, testing cost divided by final test yield, 0.95, and you get what? $4.3. $4.3. All right, so that's the cost here. Now, let's increase the area from 54 mm square to 150 mm square. So I integrate more number of transistors, in this case to make a higher capacity DRAM, 64 MB DRAM here. What happens when you go to 150 mm square? Of course, the number of dies decrease, 162, but note something else that happens here. Can you see that? Earlier the yield was 80%, the yield now is only 40%. Why? Because of the example that I showed you. When you have a higher area, there's a greater chance that there's a defect that is there in that particular area, and the IC fails here. So the yield drops to 40% here. And the number of good dies that you get are 65. And again, the package cost and all that, final cost that comes out is $29. Okay, $29. So in this case, and the company was, of course, selling it at $55, so it's making a profit. There is a market. But my point is that if you try to make it larger, the cost of the die increases for 2 reasons. One is it's occupying more of silicon, and there's a fixed wafer cost. So when you occupy more of silicon, the cost of that particular die increases. The other one is that the yield goes down, which also makes it higher here. This is another interesting example. The previous one was DRAM, and this is memory. Microprocessor, MPU, 0.35 micron here. In this case, note that the area is 90 mm square. The number of dies potentially available, 292. The yield is only 37%. Note that even though 90 mm square, but the yield is only 37%. Microprocessor is a more complicated device. Number of good dies that you get is 108. All right. So the cost of the die itself, this wafer cost divided by 108 turns out to be $17.5. Now, interestingly, look at the next number, the package cost. The package is more complicated, more complex package, 25.75 is the package cost. Even more interesting is the test cost, $35 here. And so the overall cost comes out to be $112 for this microprocessor here. $112, look at the cost breakup. The cost of the die itself is 17.5. The cost of package, very, very important. The cost of package is 25.75. And even more important, something that we don't realize, the cost of testing is so high, $35. Microprocessor is a complex entity. Memory, on the other hand, is much simpler. Microprocessor is complex and testing cost is very high. Now, if you cut down on testing, well, then there's a price that you have to pay. Now, testing is something, think about what are you doing in testing. Our 8-bit adder, how would you test your 8-bit adder? You've fabricated, done everything, right? How would you test your 8-bit adder? Well, you will apply one 8-bit input, the other 8-bit input, and see whether the output is correct or not. And how many such possibilities are there? 2 to the power 8 possibilities for one input, 2 to the power 8 possibilities for the other input. You multiply them together. How many test vectors do you have to apply? Large number of test vectors. And that's only an 8-bit adder. Microprocessor is much more complicated with multiple states and all that, right? If you economize on testing, I'm not sure anybody does that, but exactly testing any digital circuit is impossible now. The number of test vectors that you have to apply are so large that you cannot exhaustively test any digital circuit right now. It's not possible. So, if you want to read about what happens if you don't test properly, this is an example. Pentium, if you don't know that when Pentium was released, a few people noticed that there is a bug in the floating point unit. Because of the bug, the processor could return incorrect binary floating point results when dividing a number. Anyway, so there was an error in their circuit here. Intel, of course, claimed that this particular bug, would cause problem once in every 27,000 years. They had a competitor. IBM said it would occur 1 in 24 years. Intel's reputation took a hit. They had to recall all the Pentiums that they had sold, and they incurred $475, $500 million of loss there. All right, so you can imagine, you release an IC into the market, and there's a bug in it, there's an error in it, your whole reputation goes, you lose a lot of revenue here. Testing is extremely important. All right, so in fact, there's a whole area where people talk about a whole area of digital design where they talk about design for testing. You deliberately do a design in such a way that subsequently it would be easy to design. And for that, you can add additional circuitry which makes testing easy. Okay, so design cost that you see here is very important. The entire reputation of the company is depending on not releasing a IC which has errors in it. All right, so what we find is that you cannot simply increase circuit complexity. That's the point that I'm trying to make. We have a new method of making a circuit, which is an IC, but it's not simply trivial that I can go from 2K to 24K or a 64K and keep on increasing the size, because the die area increases, the yield reduces, and the cost would become unacceptable. Now, there is a possibility that what you could do is, if you cannot increase the size, what you could do is, we had that 64K circuit here, and I could partition it into 4 parts, package each one of them separately into a IC, and integrate them. So I'm making only a 8K IC here. 8K. So if I want a circuit of a complexity 64K, I can't directly make an IC of 64K because the yields are too low, the costs are too high. So what do? I partition my circuit into 4 parts. Each one of them is 8K circuit. I put them in a package and do that. Well, I can do that, but realize that if I want a 1 million transistor IC, how many such packages I will end up? And again, this method of integrating circuit is a discrete way of integrating. Again, the board size becomes large. And not only that, you see that when you interconnect this IC with this particular IC, this wire length that you see is much large. Imagine a wire length inside an IC. Wire length, because the IC is very small, the length of a wire for interconnecting one, let's say, NAND gate to the other is a millimeter. But the wire length that you see here is much larger in centimeters. And there's a penalty that you have to pay. And the penalty is in terms of delay. The wires come with capacitance. And capacitance you have to charge and discharge. So there's a penalty that you have to pay in terms of delay and power as well. So this is not a satisfactory solution. That you take a large circuit, partition it into small ICs, and then you integrate them on a PCB itself because of the problems that come. Again, the size and the weight and power and delay and all of that suffer. Fortunately, CMOS technology that I'm talking about, bipolar also, but CMOS technology is scalable. All the examples that I was giving you was for 10 micron CMOS technology. This is an example of a CMOS transistor. Don't worry about it. This is a cross-sectional view, and this is a top view layout. So this is where the gate is, and these are N+ regions, these are contacts and all that. The point that I want to make is scalable in the sense that the lateral dimensions of the CMOS transistor, vertical dimensions, you can scale. And you can scale them, both horizontal and vertical dimensions can be shrunk to not only reduce the area of each transistor, but you can make the transistor faster as well. As you shrink the transistor, the capacitors go down, and capacitances depend on the area of the transistor. So the capacitances go down, and in general, we'll see the delay goes down. So there's a big advantage that comes from shrinking the MOS transistor. It's not trivial, but you can shrink it. You can shrink both laterally and vertically, and thereby reduce the area and improve the performance. So that's the mode that people adopted. If you wanted to make a larger a more complex circuit, you can't pack more and more on the same technology. What you have to do is scale the technology. So CMOS technology is scalable. So I was giving you this particular example that we have a chip, 10 mm square, 2K transistor density. Now, suppose I go to a 6 micron technology. I shrink my transistor sizes. So from 10 micron, I go to 6 micron. As a rough rule, 3.3 becomes 2 mm. The same circuit will become 2 mm, and this will become 2 mm here. And so the whole 2K transistors will now fit into 4 mm square. Well, what would happen? My yield will go up, number of dies that I will get in a particular wafer will go up, the cost will come down. And not only that, the performance will improve. So that's one thing that you can do. You can take an existing design, and when you migrate it to a new technology, you end up getting larger number of ICs, lower cost, better performance and all that. But that's not something that people want to do. Take an existing design and shrink it. What they want to do is make more and more complex circuits, a better microprocessor. So what I can do is now, in the same size now, 3.3 by 3.3, because the technology is 6 micron here, I can now have 5.5K transistors in the same size itself. I can get double the number of transistors here. And therefore, I can make a more complex circuit without sacrificing the yield and all that, maybe at the same cost. Generally, when you go from 10 micron to 6 micron technology, the wafer cost may also go up a little bit. But roughly about the same cost, I can make a more complex IC. So if you want to make more and more complex circuits, the way to do that is, historically has been to scale the CMOS technology. Go from 10 micron to 6 micron. And early on, 1965, very early stages of integrated circuits, Gordon Moore, who was the founder of Intel, he made an observation. Looking at the integrated circuit, he said, well, this particular technology is really scalable. And he said, looking at that particular data, he said that the integration level of IC has been doubling every year at that particular point of time. And he said that looking at that particular technology at the time, he said there doesn't appear to be any inherent limitation. You can take your CMOS technology and keep on shrinking it, keep on scaling it from 10 to 8 to 6, 4, 2, and all that, and thereby you could cram more and more components onto the integrated circuits. You can make more and more complex integrated circuits without losing too much of yield and without the cost becoming too high. And so he made an observation, and this has become sort of a self-fulfilling prophecy. The whole silicon industry, seeing that this is possible, And if one company does not take advantage of that and the other company takes advantage of it, then you lose, right? So every company has followed sort of very aggressively tried to, scale the CMOS technology, pack more and more transistors and build better and better processes here. Example is Intel itself. So you can see clearly how a microprocessor is a good example of a digital circuit, a large area digital circuit. So you can see how digital circuits or microprocessors evolved. 1971 was 10 micron. 1974, Intel scaled it to 6 micron CMOS transistor. This was 2.3K transistors, became 4.5K. And look at the speed also is improving from clock frequency of 740 kilohertz to 2 megahertz. You can see here from 6 micron, they shrunk it to 3 micron, and from 3 to 1.5, right? And constantly, what you can see here, the number of transistors that you can pack is increasing. Number of transistors in an IC is increasing. The clock speed is also increasing. 1989, first time, this is a milestone, where you could pack 1 million transistors with the 1 micron technology. So you see this relentless scaling of CMOS technology. Starting from 10 micron here, 1 micron, 0.8, continuously you can see 93, 95, 97, 99, 2006. And where are we now? 2017, the transistor size has shrunk to about 22 nanometer or 14 nanometers. 14 nanometers and you get a billion transistors. So it is an old data, sort of, you can see continuous scaling. So digital design has been, the story of digital design has been a story of scaling CMOS technology and integrating more and more number of transistors, more and more number of gates to realize more and more complex functions. Okay. So digital design, coming back to, is not only logic design that you're all familiar with. So most of the digital design that we talk about is actually integrated circuit design, right? It's not simply drawing a few gates on a piece of paper or a counters and all that. It's an IC design, okay? And so it involves not only logic design, with which you're a little bit familiar, but the logic design you have to translate into a transistor schematic. And the transistor schematic has to be translated into physical layout. It also involves developing test patterns so that you can eventually test your IC, right? So digital design involves this part, of course, logic design, all this that you're familiar with, also involves transistor schematic and doing the layout, okay? Design is complex. IC design is not simple, it's complex. It requires high skill, is expensive, and is time consuming. And because of all these reasons, it's only justified if you have very high volume of ICs. Because the cost of developing an IC and the fabrication costs and all that are justified if the volumes are in millions. So if you are a designer, you are making a stepper motor controller and you need a digital circuit, right? And your volumes are, well, maybe 100 pieces or 1,000 pieces that you can sell. What do you do? Well, so traditionally, you are a person and you want to do digital design. So I'm talking about custom digital design, was carried out by interconnecting on a PCB off-the-shelf general purpose ICs. So these IC manufacturers that you see here, they made lots of very general purpose ICs, NAND gates, counters, multiplexers, all of that. They made those ICs and released it into the market. And so examples are here, NAND gates and binary adders and counters, arithmetic logic unit. And the typical digital designer would take these ICs, interconnect them, and make a system. But this is not a satisfactory way of doing it. Because, again, integrating things on a board, it becomes large. If you try to do something complex, it again becomes very large and it's slow. It consumes power. But then, so you have a design in mind and you would like an IC. But the problem is that the IC, you can't design an IC. Most people cannot design an IC. And you need very special softwares and very expensive and all that. So what do? Well, so two traditional ways that you're seeing here. One is a system designer. He or she is integrating ICs on a PCB and making it. Volumes are very low. And the other one is an IC manufacturer. Okay? The IC manufacturer's problem is can manufacture complex ICs only if volume is very high. So here is the problem. You have a system designer who has a complex design in mind. Right now, he can only integrate these ICs and do it in this way, but he's not very happy with it. He wants an IC. It's possible to design an IC, but it's going to be very expensive. The volumes are so low, right? So it doesn't justify for this particular customer designing a unique IC. So the solution to that has been programmable ICs. So digital design moved from interconnecting all of these that you see here to IC manufacturers started supplying programmable ICs, and the examples are microprocessors, microcontrollers, DSP processors. All these are very large integrated circuits with a lot of power in it. And the customer, the person that is here, can program them. Using a software, add software and program them. And instead of using a large board, you have a microcontroller and a few ICs, and then you develop your application. The other particular solution was an FPGA, a field programmable gate array. So let's stop here.